Chapter 1, Digital Systems and Information, Converting Between Number Systems. In the previous lecture, we showed how to convert from a base R system to decimal by multiplying each digit of a number by its positional weight and adding all the terms together. In this lecture, we will learn to convert numbers from decimal to binary, octal, and hexadecimal, binary to octal and hexadecimal, and finally octal and hexadecimal to binary. We are looking at objective number 3, which is to be able to convert numbers from one base system to another. In the previous lecture, we converted binary, octal, and hexadecimal to decimal by multiplying each digit by its positional weight or power series, then adding the product terms. We performed the following conversions: binary to decimal, octal to decimal, and hexadecimal to decimal. In this lecture, we will convert decimal to base R systems. If the number includes a radix point, we need to separate the number into an integer part and a fraction part since the two are converted differently. Let's first examine conversion of decimal integers. The general procedure for converting a decimal integer number to a number in base R is done by dividing the decimal number and all successive quotients by R. So R equal 2 if converting to binary, R is equal to 8 if converting to octal, and R is equal to 16 if converting to hexadecimal, until the quotient is 0. The most significant digit of our result is the last remainder collected, and the least significant digit is the first remainder collected. Converting decimal to binary. In this example, we are converting 41 decimal to binary. First, 41 is divided by 2 to give a quotient of 20 and a remainder of 1. The quotient 20 is then divided by 2 to give a new quotient of 10 with a remainder of 0. The quotient 10 is divided by 2 to give a quotient of 5 and a remainder of 0. 5 is divided by 2 to give a quotient of 2 and a remainder of 1. 2 is divided by 2 to give a quotient of 1 and a remainder of 0. Finally, 1 is divided by 2 to give a quotient of 0 and a remainder of 1. The remainders are read from last to first, where the last remainder is the most significant digit and the first remainder collected is the least significant digit. The resulting binary number is then taken from the accumulated remainders, which gives us 101001 binary. In this example, we will convert 153 decimal to octal. We follow the same procedure in which 153 and the resulting quotients are divided by 8 until the quotient is equal to 0. So 153 divided by 8 is equal to 19 with a remainder of 1. Our quotient 19 is then divided by 8, which gives us 2, a quotient of 2, plus a remainder of 3. 2 is divided by 8, which then gives us a quotient of 0 and a remainder of 2. Again, the remainders are read from last to first, where the last remainder is the most significant digit and the first remainder is the least significant digit. This gives us the resulting octal number of 231. So 153 decimal is converted to 231 octal. The conversion of a decimal fraction to base R is accomplished by a method similar to that for integers. However, instead of division by R, we multiply the fraction and resulting fractions by R. Instead of accumulating remainders, integers are collected. Also, the most significant digit is the first integer accumulated, and the least significant digit is the last integer collected. This direction is the opposite from the method for decimal integer conversion. Let's convert decimal 0.6875 to binary. First, 0.6875 is multiplied by 2 to give us an integer and a fraction. The new fraction is multiplied by 2 to give a new integer and new fraction. This process is continued until the fractional part equals 0 or until there are enough digits to give sufficient accuracy. In this case, we reached a point in which the fractional part is 0. The coefficients of the binary number are obtained from the integers, where the most significant digit is the first integer collected and the least significant digit is the last integer collected. Our result is then 0.6875 decimal is equal to 0.1011 binary. In this example, we are asked to convert 0.513 decimal to octal to an accuracy of 3 digits. We start by multiplying 0.513 with 8, which gives us an integer of 4 and a fraction of 0.104. We multiply the fraction 0.104 by 8, which gives us an integer value of 0 and a fraction of 0.832. We multiply the fraction 0.832 by 8, which gives us an integer of 6 and a fractional part of 6.656. We then multiply 0.656 by 8, which gives us an integer value of 5 and a fractional part of 0.248. We stop the process after the fourth integer, 5, which is used for rounding in base 8 of the second to last digit. We obtain our 3-digit octal fraction of 0.407 by rounding up. The conversion of decimal numbers with both integer and fractional parts is done by first converting each part separately and then combining the two answers. For example, convert decimal 153.513 to a 3-digit octal fraction. We've already done this, but we take the first part, the integer part, which is 153, and we divide by 8, which gives us a quotient value of 19 and a remainder of 1. We continue to divide by 8, and we get the quotient of 2 and a remainder of 3. Then we take the quotient 2, divide by 8, which gives us a quotient of 0 and a remainder of 2. Since our quotient is 0, we are now finished. And our most significant digit is 2, our least significant digit is 1. So our integer portion would be 231 octal. Now we take the fractional part and we multiply by 8 and we collect our integers and continue to multiply by the quotient. In this case, our most significant digit is our first integer collected, which is 4, and our least significant digit is our last integer collected, which is 5. And we are asked to go to 3 significant digits. So we will use our 4th digit, 5, to round up our 3rd digit, which is 6. So 153.513 decimal is equal to 231.407 octal. We refer to table 1.3 once again, and we'll use this table to demonstrate conversion between binary, octal, and hexadecimal. The octal number system is a power of 2, specifically 2 to the 3. Therefore, each octal digit corresponds to 3 binary digits or vectors. If you notice, in table 1.3, I have removed the leading 0 of the binary digits. So instead of 4 binary digits, we are looking at 3 binary digits. The binary number is partitioned into groups of 3 bits each, starting from the binary radix, or binary point or radix point, and moving to the right and to the left. We add a leading or trailing zeros as needed. Then assign the corresponding octal digit to each binary group. In this example, we added 1 leading 0 and 1 trailing 0 to our binary number. So 010 binary is a 2 octal. 110 binary is 6 octal. 001 binary is 1 octal. 101 binary is 5 octal. 011 is 3 octal, and we keep our radix point at the same position. 111 is 7 octal. 100 binary is 4 octal. 000 binary is 0 octal, and 110 binary is 6 octal. So our resulting octal number from 10110001111.1111000000, did I say enough zeros? 11 binary is 26153.7406 octal. Converting octal to binary requires substituting each octal digit with 3 binary digits or vectors. So 26153.74068 octal becomes 101101011.111100000010. The leading 0 is not required. The trailing 0 could be removed if the accuracy level is not necessary. Like octal, the hexadecimal number system is a power of 2, specifically 2 to the 4. Therefore, each hexadecimal digit corresponds to 4 binary digits. Conversion between hexadecimal and binary is relatively straightforward, as it was for octal. The binary number is partitioned this time into groups of 4 bits each, starting from the binary radix, then moving to the right and to the left. We add leading zeros and trailing zeros if we need. Then assign the corresponding hexadecimal digit to each binary vector. In this example, we are adding 2 leading zeros and 1 trailing 0 to our binary number. So 0010 is hexadecimal 2. 1100 is hexadecimal C. 0110 is hexadecimal 6. 1011 is hexadecimal B, and again we leave our radix point here. 1111 is hexadecimal F. 0000 is hexadecimal 0, and 0110 is hexadecimal 6. So our converted binary number becomes 2C6B.F06 hexadecimal. Converting hexadecimal to binary requires substituting each hexadecimal digit with 4 binary vectors. So 2C6B.F06 hexadecimal becomes 101100 0110101110000011, and again we could leave the trailing 0 if the accuracy requires us to leave it. The leading 0 is not required because it does not add to the accuracy of the binary number. In summary, Conversion methods between numeration systems have been seen. Decimal to binary, octal, or hexadecimal is a sequence of divisions by r, the base, 2, 8, or 16 for integers, and a sequence of multiplications by r, the base, for decimal fractions. Conversions between binary, octal, and hexadecimal is fairly straightforward since these number systems are powers of 2. And that concludes our lecture.